Have you ever just looked up at the night sky and wondered, how do we know all this stuff? I don't just mean the planets or the moon. I mean everything, like the age of the entire universe. It seems completely impossible that we could figure that out just by looking at these little tiny specks of light. Well, the story of how we actually did it is one of the greatest scientific detective stories you will ever hear.
So, before we even start, we have to get our heads around the scale of what we're talking about. When our deepest telescopes, like the Hubble, stare into a patch of what looks like empty, black sky, this is what they see. And that simple sentence right there is it's one of the most mind-blowing things we've ever learned. Almost every single one of those dots is an entire galaxy with billions of its own stars.
Okay, so step one in our cosmic investigation is to get to know these incredible islands of stars. Because, it turns out, hidden inside the simple shapes and colors of these galaxies are the very first clues we need to unravel the entire history of the universe.
Now, when you look out there, you basically see two main flavors of galaxy. First, you've got the spirals, like our own Milky Way. You know, they're flat, they've got those beautiful swirling arms, and they're just full of gas and dust. And then, you've got the ellipticals. They're more like these giant, reddish, three-dimensional footballs, made up almost entirely of old stars.
But that color difference you see, that's not just a pretty detail. It's a huge clue. So why is it? Why do those spiral galaxies have that distinct bluish-white glow, while the ellipticals are all reddish-yellow?
Well, it all comes down to this. That blue light is the signature of youth. See, spiral galaxies are like cosmic nurseries. They are constantly churning out massive, hot, new stars that burn incredibly bright and blue. And these young stars are so brilliant, they totally outshine all the older, yellower stars hanging around. Elliptical galaxies, though, they've used up all their gas and dust. The star factory is closed, so all you see is the gentle reddish-yellow glow of an aging population of stars.
For a really long time, this is kind of where the story got stuck. Astronomers could see these beautiful spiral shapes. They call them spiral nebulae, but they had no idea what they actually were. Were they just small clouds of gas inside our own Milky Way? Or were they unimaginably far away, entire galaxies just as big as our own? This question became known as the Great Debate. And this debate raged on for years, with brilliant scientists on both sides. The person who was finally going to crack this case was an astronomer named Edwin Hubble. He decided to take on what seemed like an impossible task, to actually measure the distance to these faint smudges of light. And in doing so, he was about to completely rewrite our picture of the universe.
So how do you do that? I mean, you can't just stretch a tape measure across the cosmos. Well, astronomers built something they call the cosmic distance ladder. Each rung on the ladder lets us measure farther out. First, we use radar to get super precise distances in our own solar system. Then we use that knowledge to measure nearby stars using parallax. You know, that's the effect where a star seems to shift a little bit as the Earth orbits the Sun. But to reach across the vast emptiness to other galaxies, we need the next most powerful rung on the ladder, something called a standard candle.
So what in the world is a standard candle? Okay, picture this. Imagine you see a single light bulb way off in the dark. If I tell you it's a standard 100-watt bulb, you can figure out how far away it is just by seeing how dim it looks, right? Well, in astronomy, a standard candle is any object where we know its true built-in brightness. If we can find one of those, we can calculate its distance just by measuring how dim it appears to us here on Earth.
And this is where Hubble got his breakthrough. He found the perfect standard candle. He used a special kind of star called a Cepheid variable. Now, these stars are amazing. They literally pulse. They get brighter and dimmer over and over again in a super regular rhythm. And here's the magic trick. The speed of their pulse is directly tied to their true brightness. So you find a Cepheid, you measure its pulse, and boom, you know exactly how bright that star really is.
So Hubble points his massive telescope at the most famous spiral nebula in the sky, Andromeda. He hunts around until he finds a Cepheid variable star inside it. He measures its pulse, he does the math, and what he finds is it's absolutely world-changing.
With that one calculation, he proved that Andromeda wasn't some little cloud inside our galaxy. It was a completely separate, massive galaxy, millions of light years away. The Great Debate was over. He'd solved it. But that wasn't even his biggest discovery. Not even close. Because as he measured more and more of these galaxies, he noticed something else, a really strange and totally unexpected pattern in their light. He found a pattern in the light coming from all these distant galaxies. It's a phenomenon called redshift, and what he discovered was that the farther away a galaxy was from us, the faster it was moving away from us. It's kind of like the sound of an ambulance siren. You know how the pitch drops as it speeds away from you? Well, light does the same thing. Light from a galaxy speeding away from us gets stretched out to longer, redder wavelengths, and the amount of this red shift told him the speed. Every single galaxy was moving away from us, and the farther away they were, the faster they were going. It was just shocking. The universe wasn't some static, unchanging thing, it was expanding.
And this wasn't just a vague trend, it was a perfect, clean, linear relationship. It became known as Hubble's law. A galaxy's velocity is simply its distance multiplied by a single number, what we now call Hubble's constant. This one elegant little equation turned out to be the fundamental rule for how our entire universe behaves.
The implication of this law is, well, it's profound. If everything is moving away from everything else, it can really only mean one thing. The entire universe itself is expanding.
Now, it's really important to get this next part right because it's a common misconception. The galaxies aren't flying apart through space like bits of shrapnel from some explosion in the center. No. Instead, the very fabric of space-time itself is stretching, and it's carrying the galaxies along for the ride. The absolute best way to think about it is to imagine you have a balloon with a bunch of dots drawn on it. As you blow up the balloon, every dot moves away from every other dot. There is no center of the expansion on the surface of the balloon, and from the perspective of any dot, it looks like all the others are rushing away. That's our universe.
And this incredible discovery that we live in an expanding universe leads us directly to the ultimate question. I mean, think about it. If the universe is expanding today, then it must have been smaller yesterday. And if it was smaller yesterday, it must have been even smaller the day before that. So what happens if you run the movie of the cosmos backwards? Where does it end?
Let me give you a super simple analogy. Let's say your friend drives away from your house at a perfectly steady 60 miles per hour. A little while later, she calls you up and tells you she's now exactly 60 miles away. So how long has she been driving?
The answer's obvious, right? 1 hour. It's a simple calculation. Distance divided by speed gives you the travel time. And believe it or not, we can do the exact same math with galaxies. We know their distance, and thanks to Hubble's law, we also know their speed.
But here is the most amazing part. Here's the absolute kicker. When astronomers did this calculation, distance divided by speed, for all the galaxies, all across the sky, they all gave the same answer. A nearby galaxy moving slowly and a super distant galaxy moving incredibly fast both seem to have started their journey at the exact same moment in time.
And that single starting point, that moment when the cosmic road trip began for everything, was about 14 billion years ago. Just let that sink in. By measuring the distance to galaxies and the speed they're racing away from us, we can literally rewind the clock and calculate the age of the entire universe. And that moment, when the expansion began from a single hot, dense point, well, that's what we call the Big Bang.
And this all gives us one last incredible, mind-bending idea to think about. Look back time. Because light doesn't travel instantly. When we look at the Andromeda Galaxy, which is 2.5 million light-years away, we are seeing the light that left it 2.5 million years ago. We're seeing it as it was in the past. Our telescopes, they're literally time machines. Looking far out into space is the exact same thing as looking back in time. And that leads to this final, profound thought. Because light takes time to travel, there's a limit to how far back we can see. There's a horizon in time, about 14 billion years ago, that we can never see past, the Big Bang itself. That's the edge of our observable universe. We used all the light from within that bubble to measure its age and its expansion, but it leaves us with the ultimate cliffhanger. What, if anything, lies beyond the horizon?